will start my presentation, but give me just 1 second. I don't know. I hope you can see my screen now. Okay, so let's start today's topic, which is about digital air drone photogrammetry, a tool for quantitative remote sensing. So what we are trying to explain today is how from this picture here, this landscape here, with the use of this thing here, this small machine here, we are going to achieve something like what is seen here. And before we start, I just want to give you an outline of my presentation. So the first part will be about a short introduction to photogrammetry. Then we will continue with some photogrammetric means. Then we will talk about the sensors in photogrammetry. After that, we will talk about UAVs. Then we will talk about LiDAR sensors, how we deploy a drone mission, a very short one slide only presentation about the post-processing software. And finally, I will close my presentation with 3 examples from 3 different places in this world of the world. So what is photogrammetry? Photogrammetry is a technique that uses single or multi-image photographic recordings of the 3D reconstruction and interpretation for the 3D reconstruction and interpretation of objects or areas of interest. This is a definition that it is given by Luhmann et al. In 2014. But is it only this? There are many variants of photogrammetry. For example, one variant is the extraction of accurate color ranges and values representing quantities as albedo, specular reflection, metallicity, or ambient occlusion from images of the terrain or materials in general. So in this picture, we can see an animation that was produced by photogrammetric means, where we can see the decadal change in Earth's albedo values. Now we will talk about the history of photogrammetry. Although photogrammetry was known and applied for at least 300 years, 400 years before now. Here I present you all the milestones in the evolution of the science. So in 1858, it was the first aerial photogrammetric mission that was applied by Losset, a Frenchman, using kites. And in 1862, he made the same experiment, let's say, using balloons. So he mounted his camera and he climbed on a balloon, flew over the city of Paris, and he tried to take some photos to use them in order to reconstruct the terrain of Paris, of the city of Paris, the buildings and all the other statues and landmarks that are there. In 1908, it was the first aerial expedition, photogrammetric expedition. It was the first aerial photograph that captured by plane, and it was used for mapping purposes. And this was done by an Italian captain, pilot captain, and pioneer of photogrammetry, Cesare Tardivo, where in the late 70s, the space agencies started using photogrammetry for military reasons. So it was during the Cold War that United States mainly and the Soviet Union have started deploying satellites orbiting around the globe in order to take photographs that they could use them to apply some photogrammetric means and extract information about the so-called enemy at the time. And another milestone, the last milestone until now, it was around the beginning of at the end of the first decade of 21st century, when the drone technology has lifted off, and we have all these drones flying around that they are capable of carrying cameras, etc. Before that, drones were only used by the military because they were so expensive and they were so big, and it was almost impossible for an agency or scientists to use drones for photogrammetry. So following, let's see what is photogrammetry and what is done when we are saying that we are applying photogrammetric means. So what we are trying to do is to correlate the 2D image coordinate system of each point that is defined by the camera of the acquired photograph. And by that, in today's standard, I mean the pixels. So the pixels that each photograph has, the X and Y, to combine them, use a clever algorithm and transform them by using these mathematical models into the exterior 3D object space that will give us X, Y, and Z coordinates. This definition is also taken by Forstner and Rubel in 2013. Now, what we need in order to make this photogrammetric applications is a record of a single image point must be available in at least 2 photographs. So in order to perform the above procedure here, we need to have one point that is available at least in 2 photographs. In order to have higher accuracy in all coordinates, both in X, Y, and Z, both in 3 axes, these points should be available at least to 3 or 4 photographs. So the more photographs that we have that they are depicting the same pixel, the higher there will be the accuracy of our end model. Aerial photo service with photogrammetric purpose should have 50 to 70% overlap between each acquired image pair, and recordings are different incidence angles. Similar image acquisition conditions should be applied for every picture, like light sources, shadow distribution, and camera sensor. Since each point of the generated sparse cloud is identified by its information about the geometric position and the radiometric data, e.g. the gray value, the RGB value, the gradient, and the intensity. So what is important here to remember that in order to proceed in a photogrammetric analysis of our pictures, we need to have the points the objects that we have, they have to be, we need to analyze, they have to be visible in at least 2 photographs. If we need high accuracy, they should be visible in at least 3 or 4 photographs. The more the better. There should be an overlap between each picture from 50 to 70%, at least 70%, which is, we will see it later, but we will discuss about this later. And we should have similar image acquisition conditions for every picture that we are taking. That means that we should be really careful on the light, the shadows, the gradients, etc. But yeah, now we've seen all of this, but how it is actually works, how photogrammetry works. So by using the relative position of a detected set of overlapping image points, a multi-image triangulation and space recession is performed, considering the camera calibration. So the software that it is performing the calibration and this analysis for us should know the camera calibration. If we are doing this manually, analogically, we should know the calibration of the camera. In the photogrammetric software, camera position is determined after primary sparse point cloud image triangulation by using information like camera type, focal length, and the resolution from the metadata of the images. And this is done to determine the distortions of each image. When survey information on the object surface, like the geometries and the reference points exist, the normal equations are determined and the bundle is transferred into a local or global georeferenced coordinate system, building a dense point cloud. So when the software finishes its job, it can translate all this information that has all this data that it has produced into local coordinates or global coordinates. In order to transfer the data into a global georeference coordinate system, we should give to the software extra information about real world coordinates for each picture. Now, the final adjusted bundle contains the 3D information of the measured object or area, and the quality is mainly determined by the accuracy of the reference measurements, the correlation of physical parameters of the pixels, and the systematic errors, if there are any. So as we said before, excuse me, the quality of our model is determined by these parameters and mostly by having the same image or the same pixels depicted is as many pictures as we can have. So, excuse me. Moving on the photogrammetric means, AI, where can we find data to perform photogrammetric analysis? So we can do that either by acquiring data with the use of satellites, as we said before, by the use of helicopters or airplanes, by using fixed drones, rotary drones, or by doing that on a surface mission. And this, I have it like here with this more reddish color, because this method is called close range photogrammetry and refers to the collection of photography from a lesser distance than traditional aerial or orbital photogrammetry. And here I have an example of a close range photogrammetry that I have made some years ago. So here in the left part of your screens, you can see a dense cloud. It means the raw data that the software produced from the pictures that I took and I gave as an input to the software. It generates these pixels into a cloud, a dense cloud, where here you can see the photorealistic model of a cave corridor. So it's not very accurate. There are some issues here, as you can see. There are some blind spots. There are some information that is missing. And probably this is because I haven't followed the rule. The more pictures you are taking, the better quality the image will have at the end. Now, about these means, let's see here in this comparison. Let's compare them in terms of spatial resolution. So, as it is easy to understand, the higher the spatial resolution, it means that the object should fly lower, where the lower the spatial resolution, the object should be, the camera that we are using to capture the moment should be flying higher, should be further away from the object. So here you can see that drones, both fixed wings and rotary drones, are lying in, we can achieve with these vehicles a spatial resolution of 0.1 meter to maybe 0.001 meter, where with close range photogrammetry, we can arrange more or less the same spatial resolution. Commercial satellites and airplanes, helicopters, or whatever are producing a little bit lower spatial resolution, like 1 meter or something like that, where the governmental the satellites, that they are the free satellites, they are giving us data with even lower resolution, between 100 to 1000 meter per pixel. But what about the cost? So here in the cost, we have something that is exactly the opposite with the previous category. So in terms of cost, of course, the government satellites are free, so we have no cost. Then it's the drones that the cost can be considered low to moderate. Then here we have a little bit higher cost for the close range photogrammetry, but this is due not to the equipment, but mostly because we need to spend so many man hours on the field to collect the same amount of data as we can collect with a drone or a satellite or an airplane, that they have a higher cost. Almost sometimes this cost is not something that we cannot afford for for the purposes of scientific research. What about the temporal resolution, though? As we can understand, drones, satellites, both satellites, and the close-range photogrammetry, they can give us a temporal resolution that ranges from days to months or weeks. Of course, this close-range photogrammetry, we can move it a little bit more to the right if we have someone that is willing to spend all of his time in the field taking pictures, where the aeroplanes, since they are more expensive, is somehow unrealistic to have an aeroplane flying every day or every week or even every month to collect data. And finally, the maximum spatial coverage. So for close-range photogrammetry, we can achieve a coverage between 1 square meter to hundreds of square meter, maybe more, as I said before. If we have people that they are willing to spend their time in the field, you can achieve more spatial coverage. Where with drones, this can be somewhere between hundreds of square meters to tens of thousands of square meters, where the planes and the satellites, yeah, they can move. With the satellites, we can have global coverage, and with the planes, we can have also high coverage. So now let's move on the sensors that we are using in photogrammetry. So we can divide the sensors in two categories: the active sensors and the passive sensors. Active remote sensors create their own electromagnetic energy that is transmitted from the sensor towards the terrain or the target, interacts with it, and then it is producing a backscatter emission of energy that is recorded by the sensor's receiver. So what is happening with the active sensors is that we are sending energy, the sensor is sending energy and is recording the energy, the energy afterwards. Where with the passive sensors, we can only detect the naturally emitted microwave energy within their field of view. So the field of view means that we have different type of sensors that they are covering different areas of the spectra. So these sensors can only detect the naturally emitted energy, microwave energy, i.e. the sunlight. But what are the basic characteristics for both passive and active sensors? Passive sensors, they can only be used when naturally occurring energy is available and can only obtain measurements during daytime. Of course, since we have no light, no light that is emitted on our target during nighttime, the passive sensors cannot record anything. Well, while with the active sensors, there's a different story. They provide their own energy source for illumination, as we explained before. And for that, we are able to obtain measurements day or night. And in some cases, they can even overcome obstacles. So the emitting energy can sometimes overcome some obstacles, and then we can record the backscattered emission. But is it so simple to decide which one is better, the passive one or the active sensors? No, it's not. So for this reason, I have made this small table here where I describe the advantages and the disadvantages of the passive sensors. So what the main advantages are that the only one sensor is needed since a natural emitted energy is recorded. So we don't need an extra sensor like the active ones where the one will transmit and the other one will receive. And the expeditions are time efficient. That can lead in covering wider areas because we don't have to wait or calibrate our sensors to emit the correct wavelength of the energy, etc., etc., etc. So we can only send the sensor, record this energy, the wavelength, in the spectra that we want, take back the results, and work with them. Procedures for these passive sensors are very well established with relatively easy quantifiable results. And this is because the passive sensors are actually the sensors that started. The photographic cameras are passive sensors. And because of these sensors, we started having all the science of photogrammetry. So the science of photogrammetry exists as far back as the passive sensors exist. There is no need for high computational requirements for interpretation of the collected data. It's rather simple data and not that huge in computational volume. Disadvantages for these sensors are that there is no or limited noise control on the recorded signal. We cannot eliminate the noise that we are getting when we are receiving our data. We cannot identify the source of an anomalous reading, or it can be difficult to identify the source. And the established procedures, although is an advantage, sometimes they are limiting the amount of customization that can be done to overcome some problems that we may face during our data collection. And collected data are small and usually doesn't allow for high detailed interpretation. So there are limitations and advantages using passive sensors, and one should take this into consideration. But what about the active sensors? The main advantages with these sensors are that there is better control of noise sources since the emitting signal is regulated by the user. So that means that basically that if we identify that we have something that is causing noise, we can regulate the wavelength under which our sensor is emitting in order to overcome this problem, this noise signal. Another advantage of these sensors is that active experiments provide better depth control over source of an anomalous signal, what we said before. Many different sources, different source receiver configuration can be used, enabling us for a wide variety of survey designs and customizing surveys for certain problems. Active sensor survey can produce vast quantities of data. So this is the last thing is also good and bad. But here I just put it on the advantages of these sensors because, yeah, we probably need the more data we can collect, the better it will be for our study or in order to achieve our purpose. Disadvantages. Since both receiver and transmitter are under the user's control, one must calibrate both. So that means that the equipment is more complex and it's not that easy to use. So we need to have good knowledge of what we are doing and how we are doing and how we are calibrating the sensors, both the emitting sensor and the receiving sensor. Field operations and logistics are generally more complex and time consuming for many reasons. One is the above. Another disadvantage is that many configurations of receiver-transmitter leads to greater survey cost and greater failure probability. So this is also a problem. They are not easy, and you have to calibrate. One have to calibrate and take all these parameters in order to be sure that he will collect the data that he wants. But this will make us many. He might face many difficulties both in calibrating the sensors or collecting the data, etc. And this might lead in failure about the how successful will be his mission. And as I said before, huge amount of data can become overwhelming to process and interpret. So we're getting so many data with active sensors that sometimes we cannot even handle them. Computers cannot work with this data, and then it's almost they are unusable, and one cannot not even go. I'm not even going to the interpretation step, but sometimes we cannot even process this data. So now I will present you some passive and active satellite missions that they are known. I think they are the most popular satellite missions. The first one is the RadarSat mission that was ideal for mapping vegetation, analyzing vegetated terrain and sand terrain. This project had a projected lifetime of 5 years, but operated for 18 years. This is how successful this mission was. It failed on 2013 in phase 2. The goal of this project was to produce satellite of Earth produce satellite images for Earth observation by using a synthetic aperture radar, which is of course an active sensor, and it was using a powerful microwave instrument capable of producing high quality images of the Earth during day or night, and across a wide range of weather conditions, including cloud cover, smoke, and haze. The next one is the LIS, the Linear Imaging Self-Scanning Sensor mission. RadarSat was, I forgot to mention that RadarSat was an initiative of between the United States of America and Canada, where LIS is an initiative from India, where in the LIS mission, satellites have are collecting multispectral data in 4 different bands. The spatial resolution for the visible bands, the 2 bands, and the near infrared, only 1 band, is 23.5 meters with a ground swath of 141 kilometers. So that means that the satellites of this mission are scanning with a swath of 141 kilometers, and with the first 3 with the 3 bands that they are using, the 3 sensors, the 2 are visible and the third one is near infrared, where the 4th band, which is a shortwave infrared band, has a spatial resolution of 70.5 meters with a ground swath of 148 kilometers. So the repetitivity of this mission, of LIS mission, is almost 24 days. So one satellite will pass over the same exact spot we will scan the same exact spot of the globe after 24 days. The third mission is the SPOT mission, which is an initiative from the French agency of the French agency. It stands for Satellite for Observation of Earth. SPOT is in French, are the abbreviation in French. It's a commercial high-resolution optical Earth imaging satellite system operating, of course, from space since it is in orbit. Consists of 7 satellites. It has spectral bands with simultaneous panchromatic and multispectral acquisition. The panchromatic band operates in the wavelength between 450 to 745 nanometers, where it also collects the blue, the green band, the red band, and the near-infrared band. The footprint, the swath, is almost 60 kilometers. It is a responsive satellite. It has a responsive satellite tasking with 6 tasking plans per day per satellite. So every satellite can be used for 6 different missions per day. And it has the capability of acquiring up to 3 million square kilometers daily. The last one is the Landsat. I think it's the most known satellite. This is an initiative from NASA. It was launched for the first time in 1972 under a different name, and later on was renamed into Landsat. Today we are in Landsat 8 phase that was launched on February 11, 2013. The instruments of the Landsat satellites have acquired millions of images. Most of the images that you can see online are from this mission. And the images are archived in the United States and the Landsat receiving stations around the world. And they are a unique resource for global change research and application in agriculture, cartography, geology, forestry, regional planning, etc., etc. So Landsat 7 had 8 spectral bands with spatial resolution ranging from 15 to 60 meters. Temporal resolution 16 days. And what is more important is that today, not today, but yeah, in April 2021, NASA is planning to launch Landsat 9. I guess these numbers, like the spatial resolution and the temporal resolution, will go even lower. And this is really important for anyone that wants to work with photogrammetry from satellites. So now let's move to UAVs, drones. So UAV is the most, I think is the most appropriate term to characterize these vehicles, but yeah, since everyone is using the term drone, we can, I'm using also the term drone to describe these vehicles. So unmanned aerial vehicles have gained popularity, as we said before, in performing photogrammetric missions, especially the last years. And this is due to their low cost, because it's so much affordable nowadays. They have the ability to fly and acquire data in areas that they are lacking satellite coverage, or the cost of acquiring satellite images is really high. And the drones are easy to operate, and they have the ability to carry complex equipment. So after that, one should have in mind that drones are complex systems. They are not just toys that we are used to. I think many people are treating them like this, but drones are complex systems made by hardware and software structures, and actually they are the state of the art in terms of aeronautical and software science, software engineering science. The main components of a drone can be divided into 3 categories: the aerial platform, which includes the airframe, the navigational system, the power system, and the payload; the ground control station, which allows the human control from a remote emplacement. So it is actually the remote control that we are using; and the communication system, which supports the communication between the other 2 components. So we are going to talk about this in detail now. The aerial platform is composed of different components whose purpose is to allow the flight, the flight and carry some sensors in the air for the data acquisition. The airframe is the main structure of the drone, and the key features for for building a correct airframe for a drone is the weight, the power, the communication, and control systems that we are going to place on board, and the durability to withstand forces that can occur during the flight and not cause deformation and vibration. The airframes are usually made of aluminum or carbon fiber in a way that they are lightweight and resistant. So what we are seeing in most drones, like this one in this picture, is this plastic cell that does make it look better, and it helps also in resistance of the drone to the air. So it makes it fly easier, and etc. Now, the navigation system is the main component of this drone, so this avionics is the navigation system has the autopilot that allows us autonomous or semi-autonomous flights. So in many flights, in many occasions when one is flying a drone, the autopilot kicks in, even when we are thinking that we have full control of the drone. The autopilot is doing most of the job of flying the drone. The autopilot is keeping the drone at the altitude that we want without us giving more power to the rotors, etc. So the autopilot is always there and helping the control of the drone. And then is the navigation system is composed of the flight control and the GPS or GNSS and the inner system of the drone. The flight control is the core of the navigation system. This board manages the flight planning and can verify in real time the theoretical trajectory with respect to the real one. It is possible to connect on this board several sensors to synchronize the data acquisition with the GPS type. So in this flight control sensor or software, to be more accurate, in this software component of the drone, the flight control, the sensors, the collecting sensors are linked in order to to synchronize the data acquisition with the GPS type. Then we have the GPS GNSS board. That is another very crucial and fundamental element for all the modern UAVs. Usually it's a single frequency and dual constellation GPS and GLONASS system that is installed on board. In some configuration, even a dual frequency multi-constellation receiver could be available. So more expensive drones may have more systems that they can work with. And traditionally, the receiver is only used to define the UAV position in standalone. So the standard deviation, the accuracy of this sensor is around 3 to 5 meters, and that can go lower with a new system like the EGNOS or the WOS, down to 1 to 3 meter accuracy. The raw data, the pseudo range and the carrier phase are not usually saved in this software component of the drone, but in some recent commercial systems this is also possible. And finally, we are moving to the internal system, which is mostly known as IMU. It is the last component of the navigation system, and what it's doing is always recording the distance and recording all the movements of the drone, of the vehicle. So in order to reconstruct, to understand how far is our vehicle from the pilot, from the guy that is controlling the drone. So it is controlling how much time that did the drone went up, how much time did the drone went left, right, when did it spin, etc. And by using all these measurements, it can backtrace the distance from the user, from the pilot. The power system, of course, is it's a very crucial element of UAVs. The power system is doing what it's aimed to do, is to provide energy to the system. And the power system varies according to the selected airframe. And it might, sometimes we have Wankel rotary engines, sometimes we have fuel cells, and of course that the electric solutions that they are most common, where we have multi-rotor systems. And they are using LiPo batteries, lithium polymer batteries, like these ones that they are on the screen right now. These are the cells, and this is how the battery looks like. Actually, these are the cells that even the Tesla cars are having. And then finally, we are moving to the payload. It is composed of the sensors or the instruments that they are carried by the UAV, or these two plastic water bottles that they are mounted in this drone. I don't know why. I found this picture online. And are used to and the sensors that they are used to acquire some specific data or parameter, like the RGB values in multispectral cameras, video cameras, thermal or other kinds of sensor, etc. A very important part of the payload is the gimbal, which is actually a mechanical arm that is used to stabilize the camera. So in order our photos to be clear and not having this blur effect that sometimes we are getting when we are taking pictures with our phones. Here in this image, you can see a gimbal. Usually, in the early days, the drones, they have this separate gimbal that was attached on the bottom of the drone, but nowadays the gimbal is incorporated into the drone's camera. So I think that makes them more stable and even better. Now let's move to the ground control station that ensures the permanent and interactive remote control of the UAV, informing the pilot about the progress of the autonomous flight. So the pilot is only getting this image, which is actually what we are getting from the DJI drones. Usually there's a control like a joystick for gamepad, that is connected with our cell phone, where the software is running, and into that software we can see what the drone is seeing, and not this thing. We can see actually what the drone camera is looking at, and we can see we can have other information there, like how good is the satellite signal of the vehicle, how much battery is it left in our vehicle. So yeah, green is okay. When it gets yellow, you don't have so much time. When it gets red, you have to go back immediately because the drone will fall. Here we can see how good is the communication between the drone and the remote control. Here we can see the battery, how much battery is left in the remote control, because the remote control is also working with battery. Here we can see the height of the drone, in what height the drone is flying, but this is the relative height, so how much higher from the pilot the drone is flying. And this is a value that is coming from the IMU system, as I was telling you before. This is the distance, how far in the horizontal plane is the drone from the pilot. And here is the speed under which the drone is flying. And this is the vertical speed, how fast, high or low down the drone is moving. And this is a small radar-like vision of the drone, just to where in the center is the pilot, and with the red arrow we can see the drone. So if you, in order for the pilot to spot the drone if it has lost optical optical sight with the drone, he can use this. And this is the map of the drone, of where the drone is and where the pilot is. So we can use this also to orientate ourselves when we are flying the drone. And these are some controls for the camera if someone wants to take pictures or video or whatever. The last UAV component is the communication system. This is the radio connection between the ground and the vehicle. So this is actually the communication between the remote control and the drone itself. In order to command and control the UAV, radio communication is obviously mandatory, also to assure a continuous link for emergency operations. Radio frequencies under which this communication is established are in the range of 30 megahertz to 3 gigahertz. And this is generally the radio frequency bandwidth in which small drones operate. So one should keep this in mind, because if we are in an area where there are antennas that they may transmit in this wavelength frequency, bandwidth, it might cause some communication problems between the drone and the remote control. And yeah, sometimes this is not good. It might lead to some catastrophic events. So now let's move to which drone should we choose. So when choosing a drone, one of the first questions that one should answer is whether it needs a multi-rotor or a fixed-wing aircraft. Both have advantages and disadvantages that make them better suited for certain uses. So fixed-wing drones, they look like this without the missile or anything, and might be smaller. And multi-rotor drones look like this. This is the drones that most of us have worked and have seen. So the advantages for the multi-rotor aircrafts are that they have greater maneuverability. And unlike the fixed-wing drones, multi-rotor aircraft can perform vertical takeoffs and landing. Yeah, as we can see, they also require less space to take off. They don't need to have a runway or anything. We just place them on the ground, and then they can take off, and they can hover in mid-flight and maneuver up and around the objects for easy inspection. So this is very helpful. We can decide if we want to fly the drone around an object to have a better image or whatever. And that makes them ideal for area mapping due to the number of flight legs often required to get sufficient overlap and to make high quality maps. So yeah, multi-rotor drones are better for generating, for scanning and generating high quality maps. Their price is lower because most of the drone industry have producing this kind of drones, so this has led to lower price. There is a wide price range, but one can buy a professional quadcopter for as low as $1,500, whereas a professional fixed-wing drone of similar quality can easily be 7 to 10 times more expensive than the multi-rotor drone. They are more compact, and this is good if you want to carry your drone in an area where it's not so easily accessible by car. So you have to carry your drone on your own. And this is because they don't have these fixed wings. So, and even these branches that they are holding up the rotors and the blades, sometimes they can be folded. So the drones can occupy even less space. The ease of use is also an advantage. Multi-rotor aircrafts are easier to fly for both humans and autopilots. They are so easy because we are just using this gamepad, game joystick, if I can say. It's easy. They are quick to maneuver and capable of making movements in any direction. And they have shorter learning curve for beginners that they are flying for the first time. Another thing is that they have higher payload capacity. Multi-rotor vehicles are generally support more weight due to their design. However, this means that you will need a larger and more expensive drone if you intend to carry significant payloads such as a large DSLR camera or other very special camera rigs. The disadvantages of these drones are that they have short range. One limitation of these multi-rotor aircrafts is that the flight range on a single battery probably is around 30 minutes in ideal weather conditions. And then also these drones are less stable in the wind. The aerodynamics of multi-motor aircrafts leaves them more vulnerable to wind. And this means that for cases where high winds are expected, one should have to purchase a heavier or more stable and more expensive multi-rotor vehicle, multi-rotor drone. What about the fixed wing drones? They have also advantages that they have a significant range, so they use less power, so they can fly longer and for more. And they are more stable on the air wings because of the airframe design of the fixed wing. They can sustain higher winds. So another thing is that they have safer recovery from a motor power loss. So if something goes wrong, this type of drones, they won't fall from the sky. They will continue to glide and maybe they will land somewhere safely. And they have this linear flight advantage that the fixed wing aircrafts are ideal for long distance flights, such as pipeline inspections, etc. But their capability of long flights is limited by the line of sight regulatory requirements, especially in the US and many other countries, where these line of sight regulations have been put into place after many incidents that happened with drones falling on people's head, etc. Disadvantages for these drones are that they need a larger takeoff and landing zone. Of course, they need some speed to take off, but they also need some space for them to land safely. They are more expensive. They are so challenging to fly. It's almost in some models they don't even have a controller. The user will put all the flight data and will input all the flight data into the drone, and then the drone will do its job. They are extremely difficult to fly. As we said before, they are less compact compared to the multi-rotor drones, and they are less efficient for area mapping because they have to make all these turns. So they cannot generate small turns. They have to make wider turns. So that gives them a disadvantage for area mapping. So in summary, we can see this comparison here. Multi-rotor drones, they are better in maneuverability. They are cheaper. They are more compact. They are easier to fly. They have a smaller range. They are not that stable compared to the fixed wing ones. They have higher payload capacity. They don't have safe recovery in case of a power loss. They don't need much of space for takeoff and landing, and they are efficient in area mapping. So based on this, probably one should go for the multi-rotor drone. But Now we are moving into the next question, that is, what sensors do we need? What sensors should we mount on our drone? And this is something that we should answer based on some criteria that we are making in advance. So what do we need to scan for? So what will be the output of the model? It will be a digital elevation model. What analysis do we need to perform? Geomorphological, hydrogeological, like this topic here that we are discussing today. What does the terrain look like? Do we have thick vegetation? Is it bare land? What is it? So based on that criteria, and if this criteria apply here, that we want to build a digital elevation model, geomorphological mapping, we should do our survey for geomorphology or hydrogeology, and we have thick vegetation, we should go for a LiDAR scanner. What is LiDAR? LiDAR is a method for measuring distances by illuminating the target with a laser light and measuring the reflection with the sensor. So LiDAR sensors are active sensors. How does LiDAR work? LiDAR stands, as we said before, LiDAR stands for the light detection and rating. Is a technology that has been around for many decades, but has only recently been available in size and power feasible for carrying on large drones. Excuse me. A LiDAR sensor sends out pulses of laser light and measures the exact time it takes for these pulses to return as they bounce from the ground or from the target. But it also measures the intensity of the reflection. And this is the key thing here. The LiDAR sensors are using oscillating mirrors to send out laser pulses in many directions to generate this sheet that is visible here in this picture, this sheet of light as the drone moves forward. Through measuring the time, as we said before, and the intensity of the returning pulse, it can provide readings of the terrain and of the points on the ground. So it can give us data about the terrain, vegetation, maybe, etc. So when do we use LiDAR compared to normal photogrammetry means? We should use LiDAR when we are mapping below tree canopy, like mine sites, conveyors, and other obstructions. Why? Because photogrammetry has trouble generating elevation models in areas where objects block the ground. Also, we should use LiDAR when we are modeling narrow objects, such as transmission lines, pipes, salvage features, etc., etc. And this is why, because photogrammetry has lower conformance compared to LiDAR. Where instead we should use photogrammetry when we are imaging bare earth mine sites, earthwork projects, etc. And this is why, because the drones that they are having only a camera are cheaper, lighter, and faster. And if the modeling, like in these cases, we are aiming to perform doesn't require LiDAR or higher accuracy, that will save us a lot of money. Also, if we are not getting a LiDAR, if we don't have a LiDAR sensor mounted on our drones, we are not having an expensive IMU and more accurate IMU system on the drone. We don't need that. We should perform photogrammetry when we are making a small mapping, when we are having a small mapping project, and the photogrammetry data will be okay for the needs that we are applying this methodology, because it's, as we said, it's cheaper to use this kind of drones. And we should use both in combination when we are performing modeling that requires LiDAR data. And this is when we need to have high resolution data greater than 1 meter, and can be it's almost difficult to gather this data with photogrammetry, not with LiDAR, as I say here. So here we can see an example of the same exact area. scanned with LiDAR and with photogrammetry only. The digital elevation model that came out from scanning that we performed with LiDAR and photogrammetry. Although the LiDAR provides more detail for the underneath the denser vegetation, like here, you can see how clear is with our. This is a cross section. Sorry, I forgot to mention that. This is the altitude, the height, and the distance. So here we can see with the LiDAR scanning we can even see the shape of the trees, but we can also get information about the ground, about what is lying below the trees. Where in the same area, yeah, we can see the top of the trees, but down the ground, it is becoming quite messy, and the data are not that accurate compared to those. And one should keep in mind that LiDAR pulses, they don't go through vegetation canopy. They cannot pass through the canopy, but they go around it. Yeah, they can penetrate if there are some small open spaces between the tree canopy. And mapping the terrain under the very dense vegetation is still not possible even with LiDAR. So if we have a very thick tree canopy that there is no open spaces between the leaves and the branches, and the LiDAR cannot penetrate that, then the LiDAR cannot penetrate that, and they cannot give us an accurate representation of the terrain. And here we have a comparison table for photogrammetry and LiDAR data. The costs are a little bit higher than it is today because this is an old table here. You can see that the cost for the photogrammetry is lower compared to the cost for a LiDAR drone. For the operational complexity, we don't need any additional sensors to perform a photogrammetric missions, where with LiDAR we have to have georeferenced data, and that means that multiple components of the sensors should work perfectly together. The outputs, more or less they are going to be the same, although with LiDAR we can have these intensity maps that will help us it will help us to define the vegetation and the bare land and the low vegetation and the high vegetation, etc. The accuracy for both methods is more or less the same, with higher accuracy on the elevation for the LiDAR data. And as we said before, the photogrammetry is best for mapping, surveys, broad coverage of area combined with high horizontal and vertical accuracy, where the LiDAR is better for terrain models below dense vegetation, forestry, 3D modeling of power lines, cables, etc. Now, we are moving on some guidelines on how one should deploy a drone mission. So it is important that it should be a pre-site planning before we go there and we perform our drone mission, where for this reason we can review satellites and maps, satellite images and maps in order to identify any barriers or any objects or anything that might be difficult, even small creeks, or to understand the terrain, etc. Because we also need to walk to a place that is close to the site that we are planning to scan. We should choose the right flight parameters to ensure our data quality. So this should be taken into consideration in advance. We should think in advance, what are we going to do with this data that we are planning to collect, and how high, let's say, we should fly the drone, how low we should fly the drone, in which areas should the drone cover, and if there are any hills or etc. Everything. We should maintain simple boundaries. So when one is planning to scan an area, he should keep in mind to keep simple boundaries of the area. So yeah, it's almost impossible if you have a looping boundary for your area and you are trying to scan this. Yeah, this will probably one should miss some places. It is important to overshoot the perimeter of the area that we are planning to scan. So most people say that it should be 10 to 15% in order to get a high resolution model even in the borders of our area. As I said before, we should decide on the altitude parameters. We should set a minimum 70-70 overlap between the pictures. So 70 in the lateral and 70% coverage in the lateral, in one direction, and 70% coverage in another direction of the photos. We should fly lengthwise. This is clever because then, like that, you don't need to make so much turns of the drone. That means that you will consume less battery for the drone to turn. We should divide the area into multiple missions. That will be also a case if the area is big, because like that, we can have a better control on the batteries and a better control on how many turns we need to make with the drone, etc. And of course, we should consider the packing, and we should be always prepared that something should go wrong on the field. So for this reason, it is good that when we are performing, before we perform a drone mission, we should have a backup plan for storing our data, charging our batteries. For a failure on the drone, a blade may break off in a fall or whatever. So we should have, we should pack keeping these parameters in mind. In field, we should maintain safety, and this means that we should follow the regulations that they are imposed by every country. Of course, we can wear some bright colors in remote areas or in areas that they might be hunters or whatever. We should optimize our battery life. Unless you have an unlimited collection of batteries, we should plan in advance how we will be charging the batteries, how we will rotate the batteries that we are using on the drones, etc. We should always check the data that we are collecting in the field before we go back to the office, because if we miss something, if we spot something strange, if we find a mistake that we have probably made, it is always better to fix that mistake in the field instead of going one more time back and working there. And of course, you should develop your own routine. So one that is planning to deploy drone missions should be developed in time. It will develop his own routine where he will taking all these things that I mentioned into consideration. So moving now in the post-processing software, here I have made a list with the cost and the name and the type and the OS that they are operating of these photogrammetry softwares. With Thread are two softwares that are widely used, and I actually use them both. I mostly work with Agisoft Metashape, Photoscan. Formerly it was called Photoscan. Metashape is it costs around $180, where Mesroom is an open source and it's actually really good software, and one can achieve the same results with the same ease as using the Agisoft Metashape. Pix4D is a software that is commonly used. I have never used it. And it's actually good because you can program the drone to collect the data for you. So one can go on the field, program the drone, which area wants to scan and with what resolution wants in what resolution he wants the output model to be. And he just put all these parameters into the software, and the software will control the drone later on, and everything will be done automatically. More or less, one should always keep an eye on the drone. And finally, I have here a global mapper that is only for using for performing aerial photogrammetry tasks. It can only be run on Windows OS. It's a GIS software, but the last versions they have the guys there in Global Mapper have developed a lot this photogrammetry routine, and it can produce really nice data from aerial photographs, drone photographs, and it can also handle LiDAR data as well. So now moving on, the last part of my presentation, I want to present you 3 examples where drones were used in order to decode a geological problem or geomorphological problem, an earth science problem in general. So the first one is from Thea Crossoy. She was a master student here in the Department of Earth Sciences in the University of Bergen. Her master thesis was about this area here, which is the Lomsdal-Viten National Park. And the area is somewhere here in Norway, in the middle of Norway. So there we use drones in order to find and measure some lineaments. We use this DJI drone. It's the Phantom 4 Pro drone. This is how the area looks like up here, and this is Nima. This photo here is this image that we acquired with the drone. So let's see. So one of the goals of this expedition, of this study, was to make an even better geological map for the area, because there were actually 2 different types of limestone: the yellow limestone and the yellow band, the yellow marble band, and the blue marble band. So the limestone is a marble. So we had to actually map this in detail, and this was achieved by the use of drone when we performed this high resolution photo mosaic. We developed this high resolution photo mosaic in the area, and this is how the blue slash gray band looks like, this one, and here is how the yellow slash gold marble band looks like. And this is the outcome. This is the map that came out after the evaluation of the photogrammetric data. Another thing was to generate a high resolution digital elevation model that you can see here. Actually, you can see the contours, the isolines here that running, and also they should measure these lineaments here that you can see here, that they are showing past movements of glaciers. So what we've done was we went there, she found where these lineaments can be seen. So in this area, in this area, in this area, we performed the drone mission, and then she got these high resolution images and used them in import them in ArcGIS, where she was able to delineate these lines and measure the azimuth and the inclination for each line. And then she was able to reconstruct the movement of the glacier in the area. Another part of this thesis, master thesis, was to identify depressions, to identify dolins in the area. So with blue, and we did that as a little bit of case study to test how good is this procedure, etc. So with blue are the dolins that she was able to spot on the field just by visually examining the area and walking around the area. With yellow, these shape files with yellow are the dolins that they were detected automatically by the software using the DM that we produced with the drone. And with red are the dolins that they were all, visible also there on the field, and they were detected by the automatic procedure. So here you can see the results. This is the broader, the wider, the bigger image, where you can see these small areas here. D is here, area C is here, and area B is here. So another work that I found online is by Madit et al. It is published in Marine and Petroleum Geology in 2018. And I'm quoting what they are writing in their paper. They say that in this study, they use the DJI Phantom 3 professional drone. It is important to give the characteristics of the drone for other people to perform again the same type of to perform the same methodology that someone has did. They say they present some characteristics for the drone, like it was mounted a 12 megapixel digital camera that they could tilt it from 0 to 90 degrees. So this is important. Here, before conducting the drone mapping, they selected the flight paths and the areas for its flight mission, as we said before. That is very crucial to determine all these parameters before one goes on the field, to ensure that before takeoff they were made calibrations to ensure that the platform was orientated prior to takeoff. This was just this was done to calibrate the IMU of the drone. For its flight mission, they selected the drone takeoff area generally at the top of a hill and in the center of the survey area. And probably this was done, although they are not saying it, I can understand that this was done in order to maintain the drone in a line of sight, never lose the drone from their eyes. Then they describe that they were perform their mission with the camera facing directly downwards for hilly terrain. But for some steep terrains, the camera was mounted in 45 degrees sideways to enable high quality capture of the data from the steep cliff faces. They select here, this is also important, a 70 to 90% forward and sideways overlap of the images. So they have 70% forward overlap and 90% sideways. And they carried out more than 80 flight missions, capturing a total of 4,606 pictures. And they mapped a total of area around 3.7 square kilometers in 7.5 days. So one can understand what effort is needed in order to achieve this kind of high quality result. And the drone capacity they had 6 drone batteries to use for each flight. So here you can see the generated DM, the DM that these people were able to extract from their drone data, and the orthophoto map that they extracted. You can see here some white patches that it is snow that is covering the area, as we can see here. So they were, the goals of this study was also to related with the geology of the area, to define the bedrock geology of the area. So here you can see how the area looks like, and by using these high resolution images, they were able to identify these different, probably dolomites intruding in between the marble. And here is another result map that they were able to construct by the use of their data. Finally, we're moving to Brazil, and this paper is from Silva et al. 2017, was published in Geomorphology journal. Again, I'm quoting that what they are writing in this paper. They used orthophotos taken from a UAV. They are describing here, they are putting the model of the UAV and combine them with UAV and LiDAR digital elevation models to identify cars features at different scales. The determination of flight characteristic was made for its outcrop, so they use different flight characteristic for each site that they worked. The UAV had a camera resolution of 14 megapixels and stopped above each site at a height ranging from 10 to 50 meters. So in each site, they were flying the drone, they were stopping the drone, taking the picture from a height ranging from 10 to 50 meters. And they say that in their model, each pixel of the UAV images represents 1.2 to 2 centimeter of real terrain. Excuse me. And they are quoting that their data, this type of work enabled them to acquire higher resolution data compared to the conventional orthophotos and satellite images that they are available for the area. Here, it's a picture from their results. So here you can see on the top of this image, you can see a cross section using the LiDAR point cloud. You can see the canopy, the vegetation, whatever this is, probably it's, yeah, canopy. And one can also observe the ground. But the interesting thing is that in the middle of this cross section, we can identify a sinkhole, a collapse, a collapsed dolin, that we can also detect some vegetation, the vegetation popping out from the ground of this, from the bottom of this dolin. And here is the same data after removing the vegetation. This is what I was telling you about the LiDAR data, that one can classify the reflection, the backscatter data, and can choose to dismiss or hide some of the data and work however he wants. Here, there are some really nice images from their paper where they are showing the original data and how they came out and how they worked applying some hillside techniques in order to make some features, some terrain features to pop out and be visible for them to perform their study and their final interpretation. Here are some more examples. So with this, with the aero, with only photogrammetry, we can see these C and E areas where they were able to delineate these lineaments for the C area, this area. They were able, with the drone imagery, to find and delineate these highly fractured areas, where in the E part of the image, they were able to detect some openings, some potential caves in that area. Where we, in that case, using the hypsometric data, they were able to detect some depressions on the ground. And you can see them here. So concluding, one can say that UAVs give great flexibility. They can provide great data sets if they are used properly, but there are limitations. And sometimes satellite data might be easier and cheaper to acquire. So thank you so much for your attention. Yeah.
Okay.
Hi.
Thank you very much, Dr. Penos, for that presentation. It was very, very enlightening and very interesting. At this time, we're open for questions. If we have any questions and answers that are questions that could be asked and the answers that can be given. So the floor is open. You can type your questions in the chat, or you can.
I hope I can answer the questions.
Indeed. Or you can use the raise hand feature to indicate if you have any questions that you would like to pose based on the presentation that was given. So, no questions? Well, I have one question for you, Dr. Penos. Given the information and experience you have, what would you recommend as the best outlay for the project, in this sense of using it in a karstic environment with a lot of there's a question there as well. Using it in a karstic environment where there's a lot of tree cover and not much direct access. What would be the best setup you would recommend for that situation with a very limited budget also?
It depends on the budget. That's for sure. The budget that that you are able to spend for what you want to achieve. But and also for your case there in Jamaica, I think that the tree canopy is the main. It will have it's the tree canopy should it will pose so many limitations on this type of work. So I don't know how thick it is. If it's not that thick and a LiDAR scanner can work, then a drone mounted with a LiDAR sensor, I think can achieve some great results there. But yeah, it depends on the canopy and on the budget.
Okay. Thank you very much. I see there's a question in the chat from Jose Luis Garcia. How do you identify the geoform with the data obtained?
I'm guessing Jose Luis, he's referring to the depressions, to the dolines, and that is easy. Most of these RTS softwares have this sync detection module embedded, where the software is running an analysis and it can identify closed areas where the elevation is higher on the boundaries of the area and lower in the inner part of the area. So actually, it can detect these depressions easily.
Okay. From Alison Pierce, she's asking, with dense vegetation being a limiting factor, is some form of interpolation used to derive values for areas not quote unquote seen by the LiDAR sensor?
Yeah, again, this depends on the resolution of the spatial resolution of the data we are able to obtain, and how accurate one is expecting his model to be in order to work with it. So even if we have some, I mean, in order to generate a DM, a software needs only three points with elevation data. So if there are 3 points that they are setting a surface, a plane, then a DM can be an elevation, a flat elevation surface can be formed by the DM. How accurate this surface would be, yeah, this is up to us and to define and to yeah, it's up to us to define. And I mean, one should not expect to have an accurate DM if he has 3 points that they are placed in, I don't know, maybe 100 meters away of each other. So, I mean, I don't know. I think I've answered the question.
Okay, so there could be some, but not a whole lot. You mentioned the software that you have preferred. I saw where there's a lot of free options that are available. What would determine the use of the software that you would use to analyze the data? What would determine your choice therein, separate from budget?
I mean, all softwares, they are doing theirs. I mean, all of these softwares that I presented, they can do their job. I mean, and they will perform in the same way. Then the thing is how familiar the user is with its software and what is the budget. Of course, that, as I said, there are free softwares that they are like Meshroom that you can use, that they are super easy, and there are so many guides lying around on the internet that one can find. And then it's also Photoscan and Photoscan Metashape that it has so many users around the globe, and you can ask for help, and it's so easy to use.
Okay.
Yeah.
So that's very good. All right. Michael White asks, can the drone technology be used for ground penetrating radar?
Yeah, I don't know if I don't think that yeah, there are some limitations on the height above which this ground penetrating radar should be, but some limitations compared to the wavelength. I'm not familiar with the characteristics of the emitting wavelength of this type of radars, but yeah, I think that yeah, I don't know. Also, I don't know about the weight, etc. So there are so many things that one should take into consideration. So I don't think that I can answer correctly this question. Sorry. There are so many things that one should take into consideration, and yeah, the weight should be. I think the weight is one great limitation.
Okay. Would the drone technology be applicable, or could the platform be used for anything besides visible light and near infrared? Or are those the main limitations, the main wavelengths that are used for drone technology?
Yeah, no, they are using them with LiDAR also as well. So yeah.
Okay, well, LiDAR. Okay, that's visible
Yeah,
light.
and LiDAR is laser. Yeah.
All right. Are there any further questions from anyone? Going once, going twice. All right. So with that, I would like to thank you, Christos, for a very engaging presentation.
Thank you for having me.
Believe it will be possible for us to get the presentation itself, the PowerPoint, for future.
Yep. Of course.
So you can send that to me, and I'll be able to distribute it to a person that asks for same. I'd like to thank everyone who came out to visit, WRA staff, persons from the IAEA, other environmental professionals in Jamaica, and other interested persons. Thank you so much for coming out. Please be sure to visit us again tomorrow at 10 a.m. also, where we'll have the second presentation by Dr. Aurel Perseus, looking at karst hydrology in Jamaica. And it would be great. This presentation was recorded. It'll be on YouTube as well for future viewing. And so with that, I thank you all for being here, and I'd like to wish for you all a wonderful rest of the day. And remember to sanitize and wear your masks also. Thank you very much. Goodbye.
Thank you. Bye. Bye-bye.